Today, I'm very happy to have Ofer Feinerman here. Ofer told me that he finished a master's degree in the Hebrew University in string theory. And then he went to the Weizmann Institute and did a PhD in the physics department on neuroscience. Then he went to the Sloan Kettering Cancer Research Center, where he worked on immunology. And since 2011, he's been at the physics department at the Weizmann Institute. He's been working on ants, and this is what he's going to talk about today.
Sick, and I tried to get through this talk, and I hope you can hear me well. Okay. Yeah. So today I'll talk about cooperative transport in ants. Say a bit more about what it is later. Already guessed by this picture. I'll start with a very brief introduction, and also try to connect what we do to So this talk also try to show what we do and show the connections also to physics. So we start with our motivation, kind of the leading question in our lab, which has to do with collective phenomena in biology. So in biological worlds, mostly we won't see isolated individuals, but rather it's often composed of groups of many similar units that interact to make a whole with some novel properties. For example, you have many birds that together make a flock, many nerds that make a brain, etc. In biology, they went a long way in understanding the properties of isolated individuals, proteins, animals, whatever. But groups are much more difficult to understand, and in particular, how do the properties of the group connect to the properties of the individuals of which it is formed. These are much less understood. And one way perhaps to try and approach this question is through physics. Because in physics we have quite a decent understanding of collective phenomena. We can ask ourselves how far we can take this formalism, this language that we know from physics of describing large groups, and use it to understand the connection between a bird and its flock, etc. So, well, the answer is possibly quite far. It's probably not all the way, because some things still separate these systems. And actually, those points where the physics description fails are bound to be the most interesting, or very interesting, as they will point us towards the direction of what disconnects these kind of physical systems, which we can loosely call indifferent, to these biological systems, which we intuitively call cognitive. Okay? Now, to practice this approach, we chose to work on ant colonies, as they display a vast repertoire of collective activities, but they're also very, very approachable experimentally. So in our lab, we study a large number of collective behaviors in ants, from the dissemination of information about the food source to the dissemination of the food itself around the ants. For all of them, we take care to follow all of the ants as they work towards a collective goal. And all of these I will not talk of today, and I'll be talking about cognitive transport. So actually, we're looking for a behavior that will have these two necessary properties. One, we want to provide the ants with a clear goal. And without a clear goal, they may be as indifferent as a physical system, and then we're going to miss what we want to study. Second, we want this goal to be collective. We want it to be achieved by a group of ants together. And also we want to be able to experimentally track all the ants in each ant. Again, because we're interested in how this collective behavior comes from the microscopic scales and what are the connections between these scales. Now, achieving these things together in biology, it's often not a trivial task. You typically fail if you try to be good experimentally, that the system is not natural, vice versa. So it's not always easy to find such systems, but it turns out that with the ants that we're working with, all they have to do is go to the supermarket, buy a Cheerio, and go outside and place it near an ant's nest. And then you get this. So when you place the Cheerio here, you've already created a very clear goal, which is get the Cheerio from where it is into the nest as fast as possible. These ants have to do it very fast to avoid competition. They're kind of sturdy ants, and if some other species comes along, they will give it up. So they have to get to the nest as fast as possible. The goal is a collective goal, because no single ant can move this on their own. And everything is just down below your feet. The ants are 2.5 millimeters, this species. The Cheerio is a few centimeters, so everything is very visible. Just all you have to do is film it. Another good thing, okay, so and this is what happens. So you can see that the ants cooperate together to carry the large object and move it towards the nest. And you can see how we track each of the ants. They all have numbers, I don't know if you can see it, as long as they stay in the frame. And another bonus is cooperative transport, because we want to try here physics kind of modeling. Okay, so this is a behavior of or a phenomenon of forces, of motions. So these are things we're used to deal with in physics. So the outline of the talk will be kind of a staggered outline between mechanisms and behaviors. So in the first part, we're going to try and model the ants as simple particles, kind of go with the flow, so each particle just goes, each ant just goes with the flow of all other ants. And when we try to model it this way, and kind of ironically, what we'll see is that this places the control, the simple particles that just go with the flow, places the control back with intelligent individual ants. Second, we're going to cut the individual ants for their knowledge from the system, and study the system in this way, and we'll see that without, or with the clipped ant intelligence, what we get is a system which behaves very much like a physical system. Then in the third part, we'll talk about another layer of communication in the system. So here we talked about the mechanics of cooperative transport. Now we're going to talk about the scent of cooperative transport. So the ants also lay scent marks on the floor. And we're going to see how this reveals a rich structure of feedbacks between the global and the individual scale, the collective microscopic and macroscopic scale of the system. And finally, we're going to look at one natural behavior which uses both of these and see how the ants deal with natural problems in a more full example. Okay, so let's start with mechanics of cooperative transport. So first thing that you have to know when you're carrying something big together in a group, which everybody, all of you must have done at one point or another, is that you have to have some consensus in the way you pull. Okay? So if each person, when you carry a sofa or something, pulls according to its own idea, you're not going to get very far. And it's good to have consensus. And here we have a side view of the cooperative transport. And we can see that all the ants here, you can even see it kind of slanted, all the ants here are pulling, while those in the back are lifting. So you can see that the object has an angle like this as it moves. And we're going to try to look at two simple possible explanations for this. One is smart and independent ants, and two stupid but coupled ants. So the smart independent ants, all the ants know the direction to the nest at all times, and if the nest is behind their back, they'll pull, and if it's in front of them, they lift. And the second one, the ants decide to pull or lift, so they don't know where the nest is, they're stupid, they're lost. They decide whether to pull or lift by the direction that the object is already moving. So if the object is moving towards them, they pull. If it's moving away from them, they lift. Okay? So most of them can, with the movie we saw, both of them seem to agree. And we're going to look at these two models and compare them to two observations on the scale, on the movement, of the collective movement of the entire group. So what we see here are trajectories of the load that is being carried. And we're going to look at the observations that have to do with carrying loads of different sizes. So we can give the ants loads of different sizes. You can see we shape them as rings. Why do we do this? Because this way, when we have a larger ring, we have more ants around it, and the mass per ant remains fairly constant. And this means what we're testing here is not the physique of the ants. If it was a full circle, of course, the mass per ant would grow. Not the physique of ants, but just the coordination between them. Okay, so we look at these kind of rings, and what we see here is these are trajectories of these rings from small to large. We see that this is the small item which is being carried, and the large one is here in the blue. Okay, so we see that all of them move towards the nest, but the large one moves in a much more straight line. So this is one observation. And here we look at the speed profiles of small and large item. We see that the large item is also moving faster than the small item. Okay, so we're going to look at these two observations just to begin. Now let's look at our two models. So the first one was smart and dependent. And the rule that the single ant follows here is you're smart, you know where the home is, just pull towards home, independently of the others. So that's the simple rule followed by an ant. And the collective motion is an overdamped motion. Okay, the ants are not skating, okay, they're walking. And we take that the velocity to be proportional to the total force, which is the sum of all forces by all carrying ants. And what is the consequence of this? Okay, so here we have this kind of an averaging of all the forces. And this is what is called in this field the wisdom of the crowds, which is known from this experiment by Galton, which was Darwin's cousin. I think it was the first to do it, or the first one to write a paper about it, where he brought this ox to the county fair, and then he had people independently guess the weight of the ox with a nose, so people can't talk between them. And then he took and averaged everything, like this average here, and the average was just 1 pound away, 1,197 instead of the correct 98 from the weight of the ox. This is called the wisdom of the crowds, and just the law of large numbers. The more you average, you expect to get the same mean, but smaller fluctuations around this mean. And it works. It doesn't always work, but it works in a large array of questions you can ask. And if we compare this to the item, translate it back to the items, then if we have a larger item, we expect it to have smaller fluctuations, like we saw it does move more straight, but we expect the speed to be the same. Okay? So it's a bit different than what we saw. We saw that large items move faster. And now let's look at the second model, which is going to win at the end. So actually the first model is just serving as a straw man here. We'll compare them a few more times during the talk. And the second model says the single ant rule is you're lost. You don't know where home is. You don't know where to go. So the next best thing to do to maintain consensus, pull with the current direction. And if you happen to be in the back, lift. And we take this to be a noisy kind of rule. So the ant has some tendency to follow the rule, and tendency to break it, you could say, which is this F independence. And then how does this happen? So we can model this rule by these transition rates here. So an ant which is attached, every k minus 1 second, she can redecide if she wants to pull or lift. And how does she do it? She measures the total force that she feels through her point of attachment. She compares it to this F int. And if the total force that she measured is much larger than this F int, then she will follow the rule. Okay, so if F tot is much larger than F int, the one exponent here will be very large, the other will be very small, and that will move from lifter to puller very fast, but they won't return from puller to lifter. On the other side, it will be opposite.
But you also assume here something about the velocity compared to the nature of the speed at which comes.
Yeah, the velocity will be the same. The velocity, like previously, the total velocity.
Suppose they don't carry any weight at all.
Suppose they don't carry any weight at all.
Still, they walk at a certain speed.
Right.
Or if you like, the F-top would be. There is some natural velocity at which they walk, and it should scale somehow with that velocity.
The transition rates. I mean, it will grow. I mean, if the mass will be lower, according to this model, it will move a bit faster. So the forces will be, it will change the stuff. So we played a lot with the size of the object. With the mass, we didn't play too much. We have predictions for it as well. Making it zero, I cannot do experimentally. So the ants are also very light and small. So I can't make it zero compared to their size. It doesn't exist. And on the other end, if the dependence parameter is very large, then these two exponents will be close to 1, and they'll both be equal. And then this means that the ants are very dependent. And they tend to be puller or lifter independently, with probability half independently of what the others are doing. Okay? And again, collective motion as before, as I said. And the consequences of this are here in words. So quite simple. We think that if the ants are totally non-independent, they follow this rule completely, then we get some ordered state. So all the ants in the front will be pulling, and the ones in the back will be lifting, so we get high speed and a smooth trajectory, because it also prevails from second to second, because the ants have some time scale which they decide, which is not correlated between ants. So it becomes a smooth and high speed. And if the ants are very independent, then they just start a tug of war, and ants in all directions pull. And then you get low speed and irregular trajectories, more of a random one. Okay, so we cannot really play with how independent ants are with the rule in their head. What we can do is play with the total force instead. And this model predicts that it will have similar effects. Okay, so we can look at a large object. It will give a large total force that the ants feel, and a small object will give a small total force. And then we expect that large objects move in high speed and smooth trajectories, and small ones move in low speed and irregular trajectories. Okay, so this is closer to what we see. We'll see more evidence than this later, but for now, the evidence supports more this stupid coupled model. What we can say here is that the ants are stupid, that they're trapped in this collective state with a broken symmetry, and this is how they move. They just follow each other. And this is the same species of ants when we put a kind of road around the entrance of the nest, and you can see that they went in this circle. They're just following each other around the circle, and this continued for 2-3 weeks. Okay, but there's some problem with this model. The first one, the model does not account at all for directionality, so if they're all just pulling in the direction that the rest are going, maybe they're going fast and coordinating well, but doesn't bring them to the nest. And the second one, the naturally sized objects, which are about 1 centimeter scale, have quite convoluted trajectories. And this is not clear why they're not taking the direct path to the nest. With very large unnatural objects, you can see they can move in a very straight line, but why doesn't the natural sized object move in a straight line?
Does the data give some clear scaling with the size of the object or something like that?
The what?
The variance, the function,
Yeah,
the size.
I'll show Yeah, so we think that there's a connection between the answer to these two questions. And this has to do with the leader ants. So here we see the ants carrying the object, and they're going in the wrong way. The nest is to the left, they're coordinating, but they're going up. And then an ant comes from the outside. She looks for a place to attach. Still going the wrong way. Now when she attaches, she's able to steer the group quite sharply to the left. Okay. So this is what we want to understand. How can one ant, what happens here, how can one ant take control over more ants? They have more force in her, especially if they're all pulling in the same direction. They're not canceling each other. So we looked at this, so we took our model a bit more seriously, and we tried to fit it to the motion. So now we focused on one size of an object, single size, natural size, and our model has 4 free parameters. Has many parameters, but many of them we can measure, like the mass of the object, etc. And finally, we get only 4 free parameters. And I say only because we can measure many more than this properties, features of the collective motion. Okay, we have many hours of such trajectories. We have probably more than a kilometer by today. And we can measure correlation lengths, etc. So we can fit these 4 parameters. So we fit the 4 parameters, and this is what we see. So we fit them on this natural sized object, but then once we have the model, we can easily play with the size of the object. And this is what we see. We see that if we take the same parameters, but let the ant carry large objects, what they do is this kind of a quite ballistic motion. Okay, so it has a random component, it has very long correlation lengths. It's pretty ballistic. You can see this is the projection of the speed on some axis, and you can see it has a double peak. Okay, so this means it's a ballistic motion in 2D. That's what the projection would look like. If the object is very small, you get kind of a random walk, like we see here. So now it becomes more like a Gaussian, that projection of the speed. And the natural objects are somewhere in the middle between ballistic motion and this random walk. Then we can compare this to experiment. So you can see here, this is the curvature of the trajectories in the experiment for different size objects and the simulation, and it seems to fit. Okay, so it seems like the naturally sized objects are somewhere in the middle, so they're not really random motion, but they're not really ballistic, somewhere in the middle. Okay, so we're trying to understand this more. We try to simplify the model more. So the previous model was solving the simulations. And what we did, we took a load that has just 2 sides. It has just a back and a front. It's not circular. And the ants can attach to these 2 sides and either pull or lift, as before. So we can give them spins, 1 for a puller and 0 for lifter. And then all the rest is the same. So they measure the total force, and they decide whether to pull or lift according to these exponents that we had before. But now you see why we chose them to have this Boltzmann kind of exponentials. Okay, so it doesn't really matter for the simulation, but here it will allow us to compare it to statistical mechanics. And there's translation events. So although this thing moves on 1D, it doesn't matter that it moves. Okay, so when the ants become ordered, the thing starts to move. But the interaction between the ants have nothing to do with the space. So you can really write Hamiltonian for this. Okay, so we have the Hamiltonian, which is just the regular mapping to the regular Ising model. And if we take n to infinity, while keeping this f independence over n constant, then we get the mean field solution of this model. And here the mean field is exact even because the interactions of the ants are all 12. Although the motion is 1D, each ant feels the total force over all ants. When you take n to infinity, there is no fluctuations. So this is exact. So this is for infinite n. And of course, we have the criticality here. And the ants are not infinite numbers. They're finite numbers. And to take care of this, we simply simulated this model. And for finite numbers, what we see is pretty good approximation. So again, because the connections are all-to-all, you expect mean field to be reasonable. And that's what we see here. Even down to 10 ants, we still see an ordered state in a disordered state here. Okay, so this is the blue you see, but the light blue is 10 ants. So again, our order parameter is the total force by the ants or the total speed, which are just proportional to each other. You can also see that the critical point scales with the size of the system. Okay, so what we found before is that the ants are somewhere here near the transition. Okay, so actually that animal groups are near criticality. It was hypothesized for other groups like birds, bird flocks, etc. They're typically by showing that the correlation lengths diverge. But there it was difficult to say why. So you can hypothesize why, but it was difficult to say why. Because for example, in the bird flocks, okay, so I showed before, it's not really known why they do it. Why do they flock? Then you cannot say that something is useful when you don't know what the collective behavior is for. But here we know what this behavior is for. The ants want to get home as fast as possible. And we can ask if being here helps this. And again, what we're going to do is we're going to look at an informed ant here. And what the informed ant will do, she's going to attach to the object and apply a constant force. So she doesn't care about the rule. Apply a constant force. You can see that this force is sensed by all others, so it acts just like an external field in this Ising model. Okay, so to inform the ant, these are ants that just attach to the load. They are well oriented, and the rule is you know best, all the others are lost. So just ignore the rest and pull towards the nest. And after about 10 seconds, you become like any other ant. And what does this give? So the simplified model, as we said, is just an external field. And we know that the effect diverges at the criticality. This is this red line. If you take into account that she's attached for a short time, then it doesn't diverge, it still goes up. And you can see it also in our model and in the experiment, as we saw before. So what actually guides the ants are these ants that come from the outside, that are well oriented, they know how to get home, they know exactly where they are. Ants are better navigators than humans, for example. And the group allows them to lead by being near criticality. Okay, so we can quantify this. We can see, for example, that how leaders, once a leader attaches to the group, she injects on average about 1 bit of information, helping to steer the group in the correct direction, and how the influence of this leader deteriorates after about 10 seconds. And then what this means is that leaders come and go, ants attach and detach all the time, and together they work to piece together the entire trail, aiming it towards the nest. Okay, so let's see a bit more movies. So here we see a very small item. Very small items, the ants do not coordinate. As we said, the total is smaller than the visuality parameter. We can see that this ants, once there's 2 ants here, they actually fight each other. So they go a bit left, a bit right, they slow down a lot. They can't really coordinate, they can't really get anywhere. Okay, so this is no coordination. If we take a large item, which is much larger than what the ants carry in nature, it moves in very smooth lines, as I showed before. But the moment it hits an obstacle, it's lost. So it cannot change its mind. It's a U-shaped obstacle. You have to go back 5 centimeters before going forward. It cannot change its mind. Okay, so the ants are conformist here, and this makes them also conservative, but you can't change your mind. And if you take this naturally sized object that moves in lines that are not as straight, this is exactly what allows it to get new information from these ants that come from the outside and pass the obstacle. Okay, so what we saw here that these fluctuations in the trail reflect an optimal compromise between the internal cooperation and the sensitivity to the external ants that join, external information. And the second thing we saw, that as I told in the beginning, we tried to model the ants as simple spin-like particles, and it helps us understand the system, but intriguingly, it transferred the control to ants that can navigate well and know where they are. Things that we cannot really model by physics, we have to somehow put them in. So we succeeded and therefore we failed. So what we did next is eliminate this individual intelligence from the system. And the way we did it is by adding an invisible constraint. So we want to add a constraint like we did before. We added this obstacle. But we want to add an invisible obstacle that the ants will not be able to see, and therefore will not be able to handle. Okay. You can see that this ants is not useful anymore. And how do we add an invisible obstacle? So the invisible obstacle we added is here, it's a circular obstacle here. And what we did, we just tied a very thin string from the nodes and we tether it here. Okay, so the ants can go forward until the string becomes tight. It's like they hit the obstacle, and then they cannot move forward anymore. Okay, so no ant has any understanding of this. So what happens? We let the ants go, and we see immediate consequence. Physics principles start to dominate. So they move until the string becomes tight, and then they go into this very ordered, very regular pendulum-like motion. You can see the ants running around here, they're crazy, and in the midst of all this is moving very, very order-like, because it's you'll see it's almost deterministic. And this will also help us strengthen our model compared to the other model a bit more. So first let's see this. So before we had in free motion, we had the ants were moving in the direction of the nest. In free motion, they typically move in the direction to the nest, and therefore we couldn't decide, it's harder to decide if the ants here are pulling because their back is to the nest, or if they're pulling because their back is to the direction of current motion, because they're in the leading edge. But now, when we have the nest is downwards and they're going sideways, so these directions are decoupled. And now we can see the direction of the nest is here, the ants are moving in this direction. You can see that the puller ants are in the current direction of motion and not in the direction of the nest. Okay, so if they decide to pull, not according to the direction of the nest, but according to the current motion. Let's look a bit at these collective oscillations. So we define this angle as theta. The ants can do this for hours, many hours. If it doesn't get too hot outside, if it's too hot, then they'll go home. So we can get a lot of data. We get this kind of, I think it's called shark fin shape. And what we did is we took the model from before. So the model has no notion of walking sideways or ants that hit obstacles or recognize obstacles. Same model exactly, but just had by the Lagrange multiplier, we added a constraint to it. And we modeled this. And we can see that for the coupled model, we get very similar oscillations to the experiment. Well, if we take the uncoupled model, we get something which lingers around the center. And also, we'll see later that if in the uncoupled model, the larger the object you'll take, so this again, this wisdom of the crowd, the smaller the oscillations will be. While in the uncoupled model, while in the coupled model, when you take larger items, they will tend to have larger and larger amplitudes. So again, this supports, this macroscopic behavior supports this kind of coordination. And you can see here also how well it fits. So the blue line is the experiment, so this is in theta v space. So it moves around in this cycle. And this is the simulation. And the black line is the model that we'll see in the next slide, which is a deterministic model of the oscillation. And you can see that even this deterministic model predicts it's a very nice fit. And actually the ants are going around this deterministic cycle here. But of course there is some noise because ants join, ants detach, you saw. And, so we have no control of this, but the basic phenomenon is deterministic. So let's try to understand the collective states here. So again, we take the same abstract model as before. So now the ants are moving on this semicircle here. And again, there's just a front and a back. And these are uninformed ants. And the informed ants, we just model as a constant force towards the nest G. Okay, so we call it G for the, you can guess why. And of course now that this breaks detailed balance, breaks time reversal, right? Because if there's some order, then it will move them, and then the projection of G on the, for here, for example, G has no effect because it's totally cancelled by the string. But if they move, the projection of G compared to the string changes. So the moment they move, G changes, so we have like an oscillatory driving force. So now you cannot write it's out of equilibrium, but you can still write equations of motion for the change of theta and the change of the speed. And if so the delta dt is just a v over the length, and the v dt, we can linearize it, and we get this term here. So we see there's a fixed point at v equals 0, theta equals 0. And if this part here is negative, then it will be a stable fixed point. And this happens at this relation between the number of ants and the individuality parameters. So just the same as before, except you have a correction now. And so again, just as before, you have a Hopf bifurcation when you pass this. So if they have, so for small items, with small number of ants, we expect to see some fixed stable point at zeros. And what happens for larger items? So larger item already we have some order, we have speed, but we can see, for example, by the experiment here, that for most of the time the speed almost doesn't change. Okay? So that there's abrupt changes when it changes direction, but for most of the time it changes very, very slowly. So you can approximate a change in V to be 0. Then it's useful to write the V dt, what we had before, as the derivative of some effective free energy, if you want. And this effective free energy we can just get by integrating this part here. And now you can see very simply where the oscillations come from. So here we plot this W at different angles. So at angle 0, the G is totally cancelled, so everything is symmetric. So the system is ordered. So the order parameter has to sit in one of these values here. So it shows the right, so it starts to move to the right. But when it moves to the right, then the informed ants start to have an effect. They are working against the motion. They have a projection in this direction. So they make this value smaller, this one deeper, until at some point this one becomes completely non-stable. This metastable state loses its stability, and then it flips to the other side. So this gives you this kind of deterministic oscillations. And again, for different load sizes, we expect to see different collective modes. So I showed you this before in the simulation, but I didn't show it in an experiment. It's a bit difficult to show it. A bit difficult to remove the informed ants and show it in free motion. But here we remove the informed ants without really taking them away. It's easier. We can really see how we move from a single peak, a small item, to increasingly larger double peak and larger item. Okay, so we can draw the phase space of this. And see. So this is what we saw before, the limit cycles. For big items, for small items, the ants just get stuck around here. This means this collective phenomenon. It's not that a single ant wants to walk to the side. It happens because of the coupling between the ants. And the model told us that if we have enough ants to their pulling compared to small enough number of informed ants, this means that the peak, that the valley, won't be destroyed even at 90 degrees. Even if it changes 90 degrees, it won't be destroyed. And when this happens, it will already complete a full cycle. So we didn't really believe it would happen, but we tried it. We changed the string to a stiff rod, so we can get full cycles. Otherwise, it can cut through the center. And we tried it, and surprisingly, even the direction to the nest is to the left. The answers go in circles around this.
What happened to the informed ant in this case?
Here, informed ants are here. They're always putting to the nest. So actually, the informed ant, whether it's making full circles, and they're doing this modulation of the speed. So the speed is highest when the informed ants are with the motion, and it's lowest here when the informed ants are against the motion. So they're just adding this modulation. So they're here, but there's no solution here. There's really no way to pass this kind of obstacle, but they don't do anything smart. The best thing they can do is pull towards them. Okay, so second summary. When we eliminate individual intelligence, we have a system that seems to be really enslaved by physical principles, very complex. You saw like all the ants running around. And within this, we get like something almost deterministic. And the collective states allow the group to explore beyond what the individuals gave it. So the individuals just stayed in the middle, didn't really explore, didn't really see how to pass this obstacle. Well, the group let them move to the side. Okay, so now we'll talk about scent marks. We have 1 hour or 45 minutes for this. Okay, try to go fast. Yeah, so during this process, there's another whole layer of communication, which is communication through scent marks. This is an ant laying a scent mark. So it moves a little bit to the back, sits down, and it lays a scent mark. And measure this chemically to make sure. And the nice thing about it, here you see it from the side, and you can really see that she touches the floor. But the nice thing, also if you follow the blue point, which you can see also from a top view, you can see this very stereotypic motion of the ant sitting down. And this means that even if we film an ant from the top, this is very slow down, you can see these tiny stops here when she goes backwards, and we know that this is where she lays scent marks. Like this, we can use a top camera, we can have a large field of view, and we can see the scent marks that are laid over a large surface. And this actually was never done before, so you need fast enough cameras to do it, and it was never done before. It's kind of exciting to first time to see really the scent marks that ants lay. And the ants lay these scent marks also during the motion. So here we draw scent marks and the object that is moving on them. We're not drawing the ants. You can see there's a trail here, but the object goes off it. The trail reforms here, and the object loses again, and it will reform here. So it's a very dynamic process. And this really opened our eyes once we saw this. Suddenly, you understand more than just seeing the object move on its own. So we can quantify, I won't go into this because I don't have much time, we can quantify the amount of information that a single scent mark holds to the external observer. We can quantify the amount of information, this is like 1.4 bits, the amount of information that a single scent mark conveys to the object. And these scent marks are also a means by which individual ants can become oriented. Okay, so these ants are walking around, but then they hit the scent trail, helps them orient towards the food. And the ants use this to orient. Also, when they're carried, they become lost. They let go, they can become reoriented by the same scent trail. We have an information flow here that moves between the scales. At the beginning, we saw that the carriers, single carriers, actually conform with the way that the group is currently moving. So the microscopic scale is affected by the macroscopic scale. But then we saw that this makes the macroscopic scale steered by informed individuals, single informed individuals. But these individuals are guided by the scent trail that is laid by collectively by many other ants, okay? Et cetera, et cetera. So here, in physics, many physical systems were used to the fact that you can kind of neglect the macroscopics and just look at the macroscopics of the system. But here it looks like both of them are important, and both of them are constantly influencing each other. So let's go to problem solving. So in nature, in the summer, what the ants are actually doing outside is what we're trying to do in our air-conditioned offices. They're solving problems. And here the problem is how to get this pumpkin seed to the nest in a day where you had the eucalyptus leaves falling down. You can see the ants easily pass under the eucalyptus leaf, but this thing cannot pass. So it's a little up and down motion as we saw before, and then goes back, explores some more, until they found a place to pass. So we want to understand this a bit. And to do it, we looked at a similar obstacle, but more controlled. So we have a wall like this, which can go up to 80 centimeters. The ants are 2 millimeters, I remind you. And the wall, this is the way to the nest. It's the direct way to the nest. And here there's a big opening, 2 centimeters. The ants are 2 millimeters. They can easily pass. But what they're carrying cannot pass. Okay, so if the ants just go towards home, they get stuck here. And what we see is the ants do linger for a while around this opening, but then they go to the side. They have some excursion here and pass. If you try to look at the amount of time it takes them to pass this kind of obstacles, you can see it scales pretty linearly with the width. Okay? If they did random walk, for example, then it wouldn't scale it. And we want to understand how the ants solve this problem. Okay, so first, individuals alone cannot solve this problem. Okay, why? Because individuals, again in the natural example here, they just go straight through the door, straight under this leaf. You can also see where they're laying the scent marks. They're laying the scent marks not around, but straight cross, because you're not aware how big the thing they are carrying, what exactly can be squeezed through, not squeezed through. They just mark directly to the nest, which is a bad solution in this case. And the group alone also cannot solve this. So how do we look at the group alone? Again, we try to remove the informed individuals. So informed individuals can be ones that come from the sides here. So very few ones come from the side, but this is the main road, but some of them come. And to remove them, we just block this with a wall here. And we can see that now, before it took linear time to get to the edge here, but now it will take exponential time. When we this experimentally, when we add these walls, it takes exponential time to reach 10, 20 centimeters, and they never reached much more than this. Okay, so also these oscillations that we saw before, they don't really help here. The topology of this is a bit different than the pendulum, so they don't go into these large oscillations. It gives you this exponential. So how do the ants still do it? So to look at this, we extracted all the scent marks while the ants were circumventing this object. And what we did here is we took all the scent marks from this area and put them on this chart here. So most of them pointed up, a little bit to the sides, but this, you can think of it as an arrow pointing up. So this is this area. In this area, the scent marks are like a road sign pointing to the right, and here they also point to the right. So what we see that areas in which the representation is wrong and sending them towards a dead end are quenched. Okay, so here they will always be wrong. The majority of ants will always point up, but they're localized. Okay, so it's not like every place is wrong. Okay, so the environment makes the ants wrong or give wrong advice in localized areas, which are not everywhere. The ants use this to solve the problem. Okay, so you can think of the problem that the ants face, where you have sometimes you have wrong advice. You can think of it that you're trying to go from one place to another, driving your car, but your app is stuck on walking instructions. Okay, and then the question, so you know that most of the instructions are correct. You don't see the map, you just get to turn left, turn right. So most of them are correct, but some of them are wrong. They will lead you to the end. And the question is, what do you do? Do you ignore it altogether, or what do you do? So how could you use the walking instructions to still get some information from this and reach your destination? So what the ants do, we call it the locally based ant trail. So it's actually a new kind of ant trail that we discovered. So first the ants, they lay scent marks. They start at the object and they lay scent marks, but they lay very few scent marks and stop. And then they go back to the object and they may carry it, or maybe lay some more scent marks. So the central is not from the object all the way to the nest. It's just all the time, just the next step. Okay, one step forward. The ants are also giving very local advice. Okay, so this can be like the walking instructions. So here the intelligence of the ants comes in, and sometimes they're wrong, sometimes they're correct. Very short advices. And the second, the group follows these advice, but not religiously. So here is the distance of a scent mark. Each scent mark can measure the distance at which it was laid from the object, and the time of laying. And if you see, and this is the probability that the object will actually approach it. You can see that already at 10 centimeters, there's only a 20% chance that the object will be near the scent mark. Okay, so the group follows these scent marks, but not religiously. And this is a new kind of ant trail. Okay, so regular ant trails that we used to see, they're very well defined, very long. And this happens because the ants lay all the way to the nest, and they follow them very, very strictly. That's why we get these very nice lines. This is much more dynamic. Okay, so to understand why this algorithm of the ant works, it's easy to look at the intuition from 1D. So let's say you're trying to go from A to B, and you have arrows that tell you where to go next. You don't have memory. You have arrows that tell you where to go next. And most of them are correct, but some of them are not. So possible approaches, one of them is trusting. So you say, okay, whoever put these arrows, try to be correct, try to help me. I'll just go with the arrows. But then, of course, it will take you infinite time to cross. It's not here. And it can be disillusioned. You say, okay, I don't trust this guy who put arrows. But then it's a random walk, you get quadratic time. And actually what the ant team does, it translates to follow with probability. So each time you get to an arrow, you throw the dice, and if it lands on 1 to 5, you follow the arrow. If it lands on 6, you don't. And on the stretches of good advice, which are mostly everywhere, you just get a biased random walk. So you pass them in linear time. And on stretches of bad advice, we have a few bad So it takes you exponential time, but these are also exponentially rare. So you can show that this together gives you linear time. So this was in 1D. What about 2D? So if you just want to walk east toward their direction or something like this, it's very similar to there's disordered systems where you put a voltage on them and you measure the current. Initially the current goes up, but then it goes down. Okay, so it's like moving between disillusioned and trusting. So when you're too trusting, you get stuck in dead ends. So as you can see this, I don't spend time on this too much. You can see this in disordered systems measurements. And you can measure this using, for example, tools in random walk and random environments to go towards a direction. If you want to go towards a point, towards the entrance to the nest, it becomes much more difficult to show that this works, but it seems actually to work on any graph. You can simulate it, and you can see that it works. And you can see it also, you don't need fine-tuning. You don't really need to know how much of the advice of the answer is wrong, and tune exactly your probability to follow to this, but you have a bigger range that works. Okay, so this was the first time I understood why people carry these dice in the front. Okay, so let's see again the answer algorithm at work. This is kind of the end. So what happens? So here the ants are first here, and they have the row side telling them to go up. So they try to go up for a while, but they can't. But then they throw 6, and then they don't listen to the advice, and they start going towards the right. And then they hit this row side to tell them to go right. So they're going right, right, right. And then they throw 6 again, and now they're going backwards, until they turn again, and they pass. Okay? So actually what happens is the time that they gain here from not following the advice religiously, so that they get some time here, and the time they lose here by going in the wrong direction, by doing this when the advice is good, is not as important as the time that they gain here. So altogether you get this linear rise. Okay, so we saw that here neither the small or large scale mechanisms suffice in solving these kind of confusing problems, but when you rely on both of them and the interaction between these two scales, you can get near optimal problem solving.
Well, first,
So just some, sorry?
Sorry, is there an optimal probability?
Yeah, there is an optimal probability, but as I showed it, it's not steep around it. So if you move away from it, you don't lose much. Okay. I showed it in the simulation, but it's also true. Yeah, so what we saw is we have one layer of what's happening here, and this is collective phenomena. And it seems you can use physics pretty well to understand what is happening here. We're using this actually, it's like a base for us to study this behavior. So we have one good formalism, we can start and explore from there. We have one good way of describing this using physics, but then we have to understand how to add to it these navigationally competent, goal-oriented individuals, and to understand how to quantify the information loops between these scales to understand the full capabilities of the system. This is what we understand, and this is where we want to extend it. And actually what we want to understand is this kind of group, this kind of cognitive group, what is the set of problems it can solve, and what is the set of problems it cannot solve. Okay, so to do this, we're trying to understand this theoretically, but we're also just confronting the ants with different challenges. Like you can see here that the ants have to go through this field of rocks that the ants are blind to because they can easily pass in a straight line. And you can ask yourself, okay, what is the field of, what is the set of problems, solvable problems, given this kind of mechanism that the ants can, that the ant group, the ant nest, can confront. Just thanks to the lab members, and especially Udi, Avimam, and Yael, who worked on this project, and our collaborators, Nir Gokul and Weizmann, and the Coleman group in the CNRS in Paris 7. Yeah, thank you for listening. Thank you for
Questions?
These ants are working on 2D. So how these models will change if you talk about birds that can move in 3D?
in 3D?
Yeah, well, ants move in 2D, but flocks of birds can move in 3D. So you expect the model to be different?
Yeah, which model are you talking about?
Which other models you attack any problem using flocks?
Yeah. Yeah, so the mechanical model that we use is there's some very similar flock models. So there the forces are not really forces, they're effective, like a bird sees a bird and decides if she's attracted or repelled to it. And there you can get very similar behaviors, so there's a lot of analogs. And also that they state that they can see criticality. Even though there the interactions are not far, so the ants interactions are all to all, and there the interactions are close range. So there you cannot pass through the criticality by changing the size of the flocks. So they claim that all flocks are tuning themselves to criticality, so you cannot really experimentally pass through this criticality, but apparently it's there. We can pass through the criticality by changing the size of the object from ordered to non-ordered state. And the second model I showed of following it's at least going towards a direction. It works in any dimension. And it probably works on any graph, as I said, but this is an open question. It looks very intuitive that it will work, but it's very difficult.
Is there anything we can learn from ants?
Yeah, so for example, the first example that I showed of this leadership and the ants are kind of poising themselves to criticality so they can give power to the leader. It's been used by all kind of, so I was approached by all kind of, if you talk about human endeavors, by teachers in classrooms, etc., and how to organize the class or how to organize a discussion. So also by companies, some of them try to organize the group meeting according to this. But it can also be more straightforward, like how to have a warehouse of robots. So we have just one worker who's informed, who's the smart guy, and many robots helping him. They're helping him to carry something heavy. Another thing we might learn that we saw that the leader leads, but then after 10 seconds, she stops leading. So maybe in human it translates to 10 years.
So in the latest tray that you described, how do we have any idea the mechanism how they collectively draw the dice and deciding whether to follow the...
Yeah, so some of it, so it's probably, for example, when they hit the obstacle, they cannot go forward. They can be stuck for a while, but if they, so what happens when they near an obstacle, we can kind of tell, and then show when they will leave it. And outside an obstacle, yeah. So we know they have some correlation because of they get coordinated. So when they have some direction, if there is some noise, it's hard for them to make sharp turns. So if they go a bit off the trail, they probably will go a bit more. So this may be one mechanism by which they lose it, but we still didn't connect. So we still didn't connect this very microscopic mechanical model to the kind of more zoomed out, so that we forget about the ants model of the scent marks. There's candidates for why they will use it. Either by hitting something, which they cannot continue, or by small arrows that persist for a while.
How ants ants choose to be oriented to be like the leadership and follow the other ants and like the other ants? What makes her special?
Yeah, so we think that what makes her special is the fact that she's attached. So maybe there are more special ants that are better navigators, etc. But let's take this subgroup of ants. So even these ants won't lead if they've been attached to the load more than 10 seconds. But if they've just attached to the load, and it seems as if half of the ants that attach are leaders by this. You can see really the effect. So half of the ants that attach to the load become leaders for the first 10 seconds because they're well oriented. When you carry something big, it's difficult to stay oriented. And then they will lead. And if she attaches to the leading edge, then it's very good. She will continue to pull. If she attaches in the back edge, actually what she will do, she's going to turn the whole tree around and then start to pull. So leaders always end up in the, unless another leader attached to the very near after, they always end up in the leading edge for a while, and then they get lost.
So every unattached ant could be a leader.
Sorry?
Every unattached
Ant?
ant could be a leader.
Yeah, I don't know if every, so there is, not all ants are the same, but it looks like half of them can be leaders. They just have to be newly attached.
Last question.
How similar is the behavior of different ants? Since you follow them individually.
Yes.
Are they very
Yeah, so carrying ants, first, not all ants carry. Actually, maybe 100 species around the world carry out of 15,000. And not all of these carry well. My guess is that all of these that carry well.
Between individuals.
I thought between species, yeah.
No, between individuals.
Between individuals, what is the difference? So first, they're not genetically identical. They're not the same age. Yeah.
Behaviorally, I mean.
Yeah.
How similar they behave.
Yeah. So one of them. Here it's hard for us. We don't follow them for long times outside. But some ants are lazy. Other ants do most of the work. And usually, if they do most of the work, they become better at it. They become more satisfied with themselves. They do even more of the work. So usually, there's big differences in this respect, at least. And so, ants by their life histories, they get pushed somewhere, and then they train it. They get better in it. So there's a lot of difference. Although they can pass between tasks, there are a lot of differences, even if they look the same. And then in ant colonies, there's also castes. So we may born to be a warrior, or a regular worker, and then you'll do different subsets of behaviors altogether. But even if you're in the same caste, ants will be different. It's a different personality.
Okay, so we're a little low for time. It's time for